the circuit, the light bar is on. Disconnect that, it's off. If we define connecting the circuit as 1, disconnecting it as 0, we have a binary input. If the light bar being on as 1, being off as 0, we have a binary output. This is a Boolean function. A Boolean function is a function that yields Boolean output based on logical calculation on Boolean input. They are fundamental in many research, like complexity theory, design of circuits and chips for digital computer, cryptography, and so on. Boolean function can be represented in many ways. A relatively more efficient representation may be the binary decision diagram. A binary decision diagram is a rooted, directed, acyclic graph. It is a data structure that is used to represent a Boolean function. Usually, when we say binary decision diagram, we mean reduced order binary decision diagram. If we haven't reduced that, we usually call it binary decision tree. We can apply these two rules on the binary decision tree so that we can obtain the reduced order binary decision diagram. Talking about the reduction, you might notice that for the same truth table, there could be more than one Boolean function. Namely, several Boolean functions can express an identical thing. Some of them are shorter, while some can be more verbose. For example, for this truth table, we could express the Boolean function as this. Or we could simplify this long expression as, we usually use Quine-McCluskey algorithm to minimize the Boolean function. This algorithm is functionally identical to kernel mapping. They are not hard to understand, and there are lots of materials online, so I'm not going to explain this algorithm in this video. But if you help me to make a tutorial video for Quine-McCluskey algorithm, feel free to contact me or make comments below. I could do that. This algorithm is NP-complete. The running time grows exponentially with the number of variables, so there is a limit. Of course, we don't really have to worry about that if the size of a problem is not that big. You don't have to write your own code from scratch when you implement this algorithm. There are many packages for that. And that was what I used in my quantum machine learning project. In that project, we explored all kinds of Boolean functions. The first one is AND functions. They operate AND between a pair of qubits, that is, between two qubits, and XOR functions, which operate XOR between two qubits, and parity functions. They also do XOR, but differ from the previous one. They do XOR between all input, not just a pair of qubits. They are also known as odd parity. Another one is copy function, which look at one single position of the input. If it's 1, output 1. Otherwise, it outputs 0. They copy the very one at that specific position of the input string as an output. In general, for a Boolean function, it receives the input, checks the input, then decides if it's accepted or not. If it accepts the input, it outputs 1. If not, it returns 0. If among all its input, it yields as many zeros as ones, we say it is a balanced Boolean function. In contrast, if it only yields 1 once or twice over the whole input set, that is, it only accepts 1 or 2 input strings among all the inputs, this Boolean function is highly unbalanced. If we try to learn these kinds of functions, we usually have strange learning curves. So we separate these two cases. We call it accept 1 and accept 2 function. Now, as we already knew the Boolean function, we are one step closer to the complexity of Boolean function. What's next? How should we get the uncomputable Kolmogorov complexity? I will see you in my next video.